Hello, today we're going to talk about power. Now when we say something is powerful, we mean it can do a lot and it can do it quite quickly. So that brings us to a proper definition, a proper scientific definition of what we mean by power, whether we're talking about electrical power or whether we're talking about mechanical power. Power is the amount of energy something can transfer per unit of time. So power is the energy transferred by something per unit of time. And normally that's measured in joules energy, and unit of time is the second. So normally power is measured in joules per second, and we will have an alternative unit for that, which is watts. Okay, so we're going to add it to our equations list, if I can find that. So power in watts. Okay, 1 watt is 1 joule per second. 1 joule of energy being transferred per second is energy transferred in joules divided by the time in seconds. So power is energy per unit of time, and I can put that as an equation, or a triangle rather, PET. Okay, so that's our general equation for power. Now, before I get on to defining it in terms of electrical power, let's have a look at a couple of light bulbs first. Now, these light bulbs, they're slightly different sizes, one smaller than the other. This one, you may not be able to read it, I'm not sure if you can read that or not, but it says P21W, 21 watts, 12V, 12 volts. And this one, it's even harder to read because it's not printed, it's just indented. It actually says 12V, and then it says 5W, 5 watts. So 12 volts, 5 watts. What that means is this light bulb, so this light bulb here says 21 watts. If I connect it to 12 volts, it should produce 21 watts of power as light. Well, light and heat. This one, if I connect it to 12 volts, will produce 5 watts of heat and light. They're not producing anything at the moment because they're not connected. So this 21 watts here isn't the power that it's producing, it's the power that it would produce if I connected it properly to the battery that it was expecting to connect to. If I connect it to something different, it will produce a different amount of light, it will be dimmer or brighter. So just because it says 21 watts on it doesn't mean it's always going to produce 21 watts of power. If we look at our other equations, so we've got power is the energy per time. Well, energy has also got something to do with potential difference. So potential difference was the amount of energy per charge flowing around a circuit. So if we have a certain amount of charge flowing through a light bulb, that amount of charge is going to be delivering energy to the light bulb. The more energy each charge has, the more power, the more energy is going to come out of the light bulb. Also, if we have more charges per second, so more current, then that's going to give us more energy per second because there are more charges per second carrying a certain amount of energy each. So the power in an electrical circuit is going to have something to do with the potential difference and the current at various points in the circuit. So if I measure the potential difference across this light bulb and the current flowing through it, that's going to determine the power. Okay, and the way we calculate power in an electrical circuit, it's actually a combination of the potential difference and the current. So I'm just going to give you the equation. The power in an electrical circuit is the potential difference in volts times the current in amps. So P equals V times I. P is V times I. Okay. Power is still energy per unit of time, but if it's an electrical circuit, it's a lot easier sometimes to measure the voltage and the current and multiply them together to get the power. So let's measure that then for the first light bulb. Let's do the small light bulb. We'll measure that when we connect it to a 12 volt battery. This is my 12 volt battery. This is the light bulb. I'm going to connect them together and we'll measure, well, we need to measure the current and the voltage. Okay, so I've just about connected it up, just need to connect the voltmeter, and let's see what we've got. We've got current of 0.36 amps and a voltage, potential difference across the light bulb of 12.51 volts. Current is 0.36 amps, potential difference is 12.51 volts. If I work out the power, voltage times current is 12.51 times 0.36. 36 is 4.5 watts. Okay, which is very close to the 5 watts that's printed on the side. Okay, if instead of connecting it to that battery, I connect it to a smaller battery, let's see what we get. Okay, I'm going to have to hold this on because these don't have little clips. Okay, so I'm going to take the measurements by holding that on. Okay, you can see immediately it's not anywhere near as bright, and I'm getting 0.22 amps and 5.37 volts. 0.22 amps, voltage is 5.33 volts now. Okay, so let's multiply those together. Power is 0.22 times 5.33, which is 1.17 watts. So although it says 5 watts on the light bulb, it doesn't mean it's going to produce 5 watts of power all the time. It just depends on what voltage is measured across it and what current is going through it. Now I've measured power in this case using an ammeter and a voltmeter, but in some cases it's a little bit easier to get all the measurements in one unit. So what I'm going to do is I'm going to swap the ammeter and the voltmeter out, and I'm going to use this, which is actually a dual meter, which measures energy and power and voltage and current all in one go. Okay, so it'll make it a little bit easier to measure the difference between the two light bulbs, and we can actually see the energy counting up as well, so it'll give a bit more of an indication of what's happening. So I'm going to set that up now. Okay, so I've connected up my dual meter, okay, and that's showing, let's see if I can get the display light a bit better. There we go. That's showing no joules, no watts, no volts, no amps, because I haven't actually connected it to the battery. If I connect it up now, okay, the light bulb comes on. It's saying 4.7, 4.6 watts, and what you can see underneath, the joules are counting up. Okay, so it's counting up in joules the amount of energy that's being transferred to this light bulb. That's basically what's being put out as heat and light from the light bulb. So if I reset it in a second and I count for 10 seconds, okay, that's 1, 2, I'll wait till I get to the 7. So about 7, that will be about 10 seconds. Okay, and then I'll disconnect it. Okay, I didn't quite connect it and disconnect it in time. 47 joules in about 10 seconds. So that was about 4.7 watts. Okay, but that was the small light bulb. If I connect up the bigger light bulb, okay, the bigger light bulb is brighter. And you can see it says 22.77 watts or 22.7 watts, or give or take. And you can see the energy is counting up a bit more quickly. Let's see. Oh, there we go. That's showing it quite nicely. So 22.5 watts. It said on the side 22 watts, I think, or 21 watts. So it's around about the right amount. And you can see the energy is counting up quite quickly. So let's see if I can do the same thing again. We'll reset it and we'll count for 10 seconds. And then we'll stop it after 10 seconds, which is about now. Okay, 227 joules in 10 seconds, which was about, so there we go, you can see 227 joules in about 10 seconds, which is about 22.7 joules in 1 second, which was about 22.7 watts. And that's what it said on the power meter as well. Okay, so that was the power of the light bulb when I had it connected to the correct battery. If I connect it to a different battery, like this one, let's see what we get this time. It was 22.5 watts before. I connect it this time and we get, well, it's barely lighting up. Just about see it lighting up. And it's only producing 3.2 watts. And again, you can see the energy, the joules, counting up much more slowly. That was for a light bulb. What about a resistor? Resistors are not designed to produce light. They're just designed to produce a certain amount of current flowing if you put a certain voltage across them. They're not producing light, but they still transfer energy. Where does that energy go? Well, it just goes to heat, really. It heats up the resistor. Sometimes you want that, sometimes you don't, but it doesn't matter whether you want it or not, you get it. So I've connected that up in place of the light bulb, and it's giving me 1.6 watts, 15 joules, 16 joules, 12 volts, 0.13 amps. So it's about 1.6 watts is being produced or being transferred by that resistor. It's not obvious that anything is happening at all. There's only one way, really to see what's happening, and that is to use something like this, the infrared camera. But that resistor, you can see, is quite hot. Okay, it says 31 degrees C, everything else around it is 23 degrees or so. Okay, so that resistor, in fact, that resistor says 73 degrees. It's actually much hotter than I thought. It says 74 degrees. It's getting quite hot. Why is that getting hot? It's because it's transferring energy. Okay, let's see if I do the same with a different resistor. Okay, this resistor is 150 ohms instead of the 100 ohms that we had last time. And let's see what we get here. Okay, we get 1.05 watts, so not as much, but let's see, is it getting as hot? It is still getting hot, and it's warming up. It's just not as hot as the last one. Something you can notice, this resistance, this crocodile clip there is actually getting warm as well. Presumably that's got a slightly higher resistance than it should have. The wire is actually it's actually heating up in a way that it shouldn't. But the resistor is actually getting quite warm. Okay, that's because it's dissipating a certain amount of power, a certain amount of energy per second. So how would we work out the amount of power that was being transferred by that resistor, the amount of power per, or amount of energy per second? Well, we would need to know the current and the voltage, the current through the resistor and the voltage across it. This was my circuit, and the first resistor was 100 ohms. I had a 12 volt battery, approximately 12 volts. Now, what would the current be through that resistor? Well, we've already used our equations for current. Okay, current or resistance with current in it is potential difference over current. So the current is the voltage divided by the resistance. So the current would be V over R, which is 12 volts divided by 100, which is 0.12 amps. That means that the power is the voltage times the current, which is 12 times 0.12, which is 1.44 watts. Okay, and that's approximately what we were getting on the power meter. So it's 1.44 watts. If I had the other resistor, which was a 68 ohm resistor, I think it was, then I get, oh no, it was 150 ohms, 150 ohm resistor. Then I would have had 150 ohms. Current is the voltage divided by resistance, which is 12 volts divided by 150 ohms, which I have to do on the calculator this time. 12 divided by 150, which is 0.08 amps. And I get then that the power is 12 times 0.08, which is 12 times 0.08, 0.96 watts. And the power meter we had was measuring about 1 watt. It was almost exactly 1 watt. Okay, so one final thing is to see what happens if I put two resistors in series. Let's have a work out first what should happen. Okay, so let's try two resistors. My battery, 12 volts. And I'm going to put a 150 ohm and 68 ohms, just because I happen to have those two. Okay, I've got 150 ohms and 68 ohms. So I'm going to use those. Now, I need to find out what current is going to flow. Well, resistance, the total resistance in the circuit is 150 ohms plus 68 ohms. So the total resistance is 150 plus 68, which is 218 ohms. Okay, 12 volts is the voltage. So current is therefore 12 volts divided by 218 ohms, which is 12 divided by 218, 0.055 amps. Okay, 0.055 amps. Now, what I now need to know is what's the voltage across each of these. Okay, so 0.055 is flowing around the whole circuit. But 12 volts is not measured across the 150 ohms, and it's not 12 volts across the 68 ohms either. The thing that I do know is that I've got 0.055 amps going through 150 ohms. Now, to find out how much power there is being produced by each resistor, I'm going to combine two of the equations together. I'm going to combine my power is voltage times current, and I'm going to also use that the voltage is the current times resistance, which was one of our other equations. Okay, so the current, sorry, the voltage is the current times the resistance. If I take this equation and replace V in the top equation with IR, then I get P equals IR, which is the same as the potential difference, times I, which is I squared times R. And this is a way to calculate the power in each of these resistors if you know the current through them, but you don't know the voltage across them. What it is, it's a shortcut way of first calculating the voltage across that resistor by using V equals IR, and then using that to multiply by the current to get the power. It's just a shortcut way of doing it. So it's so important, I'm going to add it as a third version of the power equation. So power in watts is the current in amps squared times the resistance in ohms. Okay, so P equals I squared times R. Okay, so let's calculate it for each of these. For the 150 ohms, I get P equals I squared R, which is, well, it was 0.055 squared, so 0.055 squared times 150 gives me 0.454 watts. For the 68 ohms, I get P is I squared R, which is 0.055 squared times 68, which is 0.206 watts. That means that there's more power in the 150 ohm resistor than there is in the 68 ohm resistor when they're connected in series like that. If this is less power, then this should get less hot, and we ought to be able to see that on the infrared camera. So let's just do that as a final test. I'll set it up and then we'll have a look at it with the camera. Okay, so I've connected that up. I've got the 68 ohm resistor here. I've got the 150 ohm resistor here. The 68 ohm should be producing about 0.2 watts of power. The 150 ohm should be 0.45 watts. So this one is producing more energy per second, more power. It should be getting hotter. Okay, so the bottom one, it says 37.8 degrees, and the top one 44.8 degrees, 44.9, and still going up. So you can see that the top resistor, which is the, if I lock the temperature there, okay, the 150 ohm resistor, which is the top one, is hotter than the 68 ohm resistor. It's developing more power in the 150 ohm resistor than the 68, and that's why it's getting hotter. There's nothing visible in the circuit, but that's the proof that the power is different in the two. So there you go. Power is defined as being the amount of energy transferred divided by the time taken. So that's the energy per unit of time measured in watts. For an electrical circuit, we can also calculate it as the potential difference across something times the current through it and measure that in watts. And occasionally we don't have one of these two, but we have the resistance, in which case we can use our Ohm's law equation to calculate the missing one of the potential difference or the current. So that gives us a third equation, which is very useful for current flowing through resistors or resistances, like wires, where the current squared times the resistance, I squared R, gives us the power in the wire. And the more power that's being developed, more power that's being transferred, the hotter the resistor will get in general, which is why a high power lamp will get brighter than a dimmer lamp, one which is less powerful.